Before talking about permutations and combinations, it is important for us to introduce the multiplication principle, which you may have seen before. Let P be a process consisting of k steps. If there are n1 ways to carry out step 1, and 2 ways to carry out step 2, and so on, until we have nk ways to carry out step k, then there are n1 times n2 times all the way to nk ways to carry out P. It just means that we have to multiply the possibilities for each step to get the total number of possibilities for the whole process. Let's look at an example. Suppose a password consists of 5 characters. The first 2 characters are capital letters, and the last 3 are digits. For example, AB074 can be a password of this type. We want to find the number of possible passwords if A. There are no restrictions, and B. Where all characters are distinct and the last digit is odd. For part A, since there are no restrictions, and we know that there are 26 capital letters and 10 digits in total, the number of possible passwords is 26 times 26 times 10 times 10 times 10, which gives 676,000. For part B, since all characters are distinct, after picking the first letter, where there are 26 of them, we have one less digit to choose from for the second letter, so the number of choices for the second letter is 25. As for the digits, since we require that the last digit is odd, we need to choose the last digit first. Since there are 5 odd digits, namely 1, 3, 5, 7, and 9, there are 5 choices for the last digit. Now, when we pick the first digit, we have one less digit to choose from, since we have already picked the last digit. So there are 9 choices for the first digit. Similarly, when we pick the second digit, there are 2 digits already chosen, so we have only 8 choices left. The answer is 234,000. Now let's consider the letters A, B, C, and D. In how many ways can we arrange them side by side? For example, ABCD or BACD. Let's draw for ourselves 4 horizontal lines to indicate the positions of the 4 letters. For the first letter, there are 4 choices for us to choose from. Once we have picked the first letter, there are 3 choices left for the second letter, and 2 choices left for the third, and then the remaining letter must go into the last position. So there's only one choice. By the multiplication principle, the number of ways that we can arrange these 4 letters is 4 times 3 times 2 times 1, which is 24. Observe that this expression is the same as 4 factorial. We say that each arrangement is a permutation of the 4 letters. In general, the number of permutations of a set of n elements can be found using a similar approach. For the first element, there are n choices. For the second element, there is one less element to choose from, so there are n-1 choices. For the third element, there are 2 elements already used, so there are n-2 choices. This carries on until we have 3 choices for the n-2nd element, 2 choices for the n-1st element, and the last element must go into the last position. We recognize that this expression is precisely n factorial. Now consider 6 letters A, B, C, D, E, and F. We are interested in finding the number of 4-letter permutations. In other words, in how many ways can we pick any 4 letters out of the 6 and arrange them side by side? Again, first let us draw 4 horizontal lines to indicate the positions of the 4 letters. For the first letter, we have 6 letters to choose from, so there are 6 choices. For the second position, since we have already picked one letter, there are 5 letters left, so there are 5 choices. Similarly, there are 4 choices for the third letter and 3 choices for the last letter. Again, by the multiplication principle, the number of permutations is 6 times 5 times 4 times 3, which is 360. Observe that the expression is the same as 6 factorial divided by 2 factorial. In general, the number of permutations of R elements from a set of n elements can be found using a similar approach. For the first element, there are n choices. For the second element, there is one less element to choose from, so there are n-1 choices. For the third element, 2 elements are already used, so there are n-2 choices. This goes on until the rth element, where we have n-r+1 choices. We note that this expression is the same as n factorial divided by n-r factorial. Now, let's consider again choosing 4 letters from A to F, except this time the order does not matter. For example, ABCD is the same as BACD. How many choices are there? We use a large bracket with the number 6 on the top and 4 on the bottom to indicate the number of choices, where the bracket is pronounced as 6 choose 4. We are going to find the number of permutations of 4 letters in 2 steps. Step 1, we need to choose any 4 letters out of the 6, and the number of ways to do so is exactly 6 choose 4, because we do not care about the order in which we choose the 4 letters. Step 2, we are going to arrange the 4 letters side by side, and the number of ways to do so is 4 factorial, as we have seen earlier in this video. By the multiplication principle, the number of permutations of 4 letters, which we know is 6 factorial over 2 factorial, is the number of choices in step 1 times the number of choices in step 2. So we can set up the equality 6 factorial divided by 2 factorial equals 6 choose 4 times 4 factorial. Rearranging, we see that 6 choose 4 equals 6 factorial divided by 2 factorial times 4 factorial. And this is the answer that we wanted. We say that each choice is a combination. It's not hard to realize that we can generalize the argument to find the number of combinations of R elements from a set of n elements, and the expression is n factorial divided by R factorial times n-r factorial. Again, this number is denoted by a large bracket with n at the top and r at the bottom, and this is pronounced as n choose r. Lastly, we introduce the Binomial Theorem, which states that for any real numbers a and b and positive integer n, a plus b raised to the power n equals the sum of n choose r times a to the n-r times b to the r from r equals 0 to n. There are many proofs of this result, including the use of mathematical induction. Here we will just present one of them. We first write a plus b raised to the power n as a plus b times a plus b, and so on, repeating for n times. We observe that all the terms in the expansion are of the form a to the n-r times b to the r, where r is a value in 0, 1, 2 up to n. For each r, in order to get the expression a to the n-r times b to the r, we have to choose b from r of the brackets and a from the remaining n-r brackets. So the coefficient of a to the n-r times b to the r is the number of ways of choosing r brackets from n brackets, which is n choose r. And this completes the proof. As a result, n choose r is also called the binomial coefficients, since they appear as the coefficients of a binomial expansion.